Highly specialised plants that can develop along sheltered coastlines form important habitats like mangrove forests, seagrass beds and salt marshes. We value them as places to relax and recuperate. They are rich in animal and plant life. They absorb CO2 from the atmosphere and trap it beneath the ground. They even protect our homes and our livelihoods from coastal flooding. Sadly, salt marshes have been severely impacted by coastal development, and there are fears that already degraded sites could succumb to the impacts of climate change. Sea level rise in particular has been identified as a potentially existential threat to salt marshes around the world. Since the 1970s, there's been a lot of research into how salt marshes will survive sea level rise, and before making any predictions, researchers needed a thorough understanding how plants interact with their physical environment to build a salt marsh from the bottom up. Imagine we're at the coast, in a place which is sheltered from large waves and strong currents. During disturbance-free periods, salt marsh plants like the common cordgrass Spartina anglica might establish, starting the development of the salt marsh. The first plants that colonise tidal flats are called pioneer plants. The plants slow the flow of water during flood and ebb tides, which allows sand and silt washed in by the tide to accumulate and settle around the plants. By capturing this sediment, the marsh begins to grow vertically with each tidal cycle. Plant roots bind the soil and add sticky organic material into the ground, making it resistant to erosion and helping it to grow vertically. And as the marsh grows vertically, it's submerged less frequently by the tide, allowing other marsh plants to establish, creating distinct plant zones along the length of the marsh, each with its optimal niche between mean high water neap and mean high water spring tides. The change from a low elevation tidal flat to a high elevation salt marsh is an example of a regime shift. And that shift occurs because of a positive feedback between plant growth capturing more sediment, which improves plant growth, which captures more sediment, and so on. Because pioneer plants like Spartina anglica are so important in building the salt marsh, they're referred to as ecosystem engineers, and so deserve special attention in terms of understanding how salt marshes will likely respond to climate change. Interesting fact, Spartina anglica is actually a new species. It became fertile after mutating from its parent hybrid Spartina townsendii, a cross between the native and the North American Spartina species. It was brought over in ships ballast water in 1870. Spartina is able to survive lower on the intertidal than any other salt marsh plant, and so it was quickly identified as a really good way to reclaim land from the sea by coastal engineers. It was exported and planted around the world. These images show how Spartina was planted on a tidal flat in the Netherlands. In only 20 years' time, the Spartina has grown to a closed sward, and the land could then be reclaimed and drained for agriculture and construction. So now that we have an understanding of how salt marshes form, how do we think that salt marshes will respond to sea level rise? All they need to do is grow vertically with the rate of sea level rise, right? We also need to consider what happens at the tidal flat right in front of the salt marsh. There are no plants here, so sediment accretion rates are much lower, and any sedimentation which might settle is more easily washed away since there are no plants to hold it in place. If we consider the salt marsh and tidal flat together, 4 possible scenarios can happen under sea level rise. Scenario 1. Enough sediment is transported onto the coast, say from longshore drift, that more sediment accumulates on the tidal flat than is washed away. The tidal flat and the salt marsh both grow with sea level rise. Scenario 2. If the sediment transport is large enough, the tidal flat and salt marsh expand seaward. Scenario 3. If the sediment transport is low, what little sediment there is in the water column is captured by the marsh surface but not the tidal flat. So the marsh grows, but the tidal flat doesn't. Deeper water above the tidal flat means that larger waves can reach the marsh edge, causing erosion. And we get a fascinating scenario where the erosion of the marsh edge can actually supply the marsh surface with sediment, helping it to grow vertically. This process has a grisly name: auto-cannibalism, the marshes eating itself to survive sea level rise. And finally, scenario 4. The rates of vertical accretion are so low on the marsh surface that plants can no longer tolerate the waterlogging and they die. The sediment is exposed to erosion and the soil washes away. So which scenario is playing out around the world? Well, it's different for different locations around the globe, depending on the rate of sea level rise and the availability of sediment. Marshes in the Mississippi Delta, for example, are famously sinking because there's not enough sediment reaching the coast after a canal was built to channel floodwater straight to the sea and protect New Orleans from river flooding. Which is ironic in a way, because the salt marshes are sinking, they're no longer able to protect New Orleans from coastal surges. This is an example of scenario 4, where the marshes are drowning. Across Western Britain, salt marshes have been expanding in recent years, presumably because there's enough sediment reaching the coast to drive marsh expansion, as in scenario 2. Two papers, published in 2016, attempted to find out if marshes were growing vertically with sea level rise around the world. Interestingly, both came to different conclusions. By 2100, Crosby et al. Predicted that as much as 90% of the world's marshes could be lost to sea level rise, whilst Kilruan et al. Predicted that marshes, for the most part, would survive. Even if marshes, for the most part, can keep pace with sea level rise, we don't know if the marshes are prograding or eroding laterally. Remember scenarios 2 and 3. Moreover, conditions change over time. The rates of sea level rise at the moment, for example, are around 3.7 millimetres a year. And in 100 years' time, this could increase to 8 or even 16 millimetres a year, depending on how rapidly the climate warms. The flow of sediment to the coast could also change as dams are built, or as longshore currents change. Salt marshes could therefore shift from one scenario to another. So we have a good understanding of what might happen to the front of the salt marsh facing the sea as sea level rises. But what about the back of the marsh? Will that land flood? Will the marsh be able to retreat inland as sea levels rise? In short, yes. In fact, this process has happened for thousands of years as sea levels have fluctuated naturally with the freezing and thawing of glaciers during ice ages. Studies have found that marsh deposits are rarely older than 6,000 years, suggesting that the marshes are always being eroded and relaid as mean sea level moves up and down the coast. Along the eastern seaboard of the US, for example, forests are drowning as the sea level is rising and the marsh is establishing among the dead tree trunks. They'll soon form petrified forests like those which are occasionally uncovered by storms along our coastline. But for most coastlines around the world, especially Europe, we've built and developed along the coastline, meaning there's nowhere for the marsh to retreat to. Most of salt marsh loss has actually been because of land reclamation, the process of building sea defences at the front of the marsh to drain the land behind for agriculture and construction. Over 85% of estuaries across Britain have been subjected to reclamation and now have some kind of sea defence at the back of the salt marsh. So for many places around the globe, salt marshes are stuck between sea defences and rising sea levels. This phenomenon is called coastal squeeze. There's still a lot of uncertainty about how salt marshes will respond to sea level rise in the future. But a study published in 2018 by Shuesh et al. Predicted that at worst, 30% of coastal wetlands around the world could be lost by 2100. At best, and if we take reasonable steps to open about 40% of the coast to the sea and don't interfere with the natural flow of sediment to the coast, coastal wetlands could actually expand by up to 60%. To make this a reality, Governments and NGOs are working on preserving, restoring and recreating salt marshes. In the Mississippi Delta, a $250 million project is hoping to restore the flow of sediment to the marsh. In the UK, nearly 3,000 hectares of intertidal habitat have been created since the 1990s in a process called managed realignment, where old cedar fences are breached, allowing the tides to flow into abandoned farmland for new marshes to take hold. Other initiatives like seed planting, sediment recharge and wave breakers are also being used to protect and restore salt marshes. The future is by no means secure for salt marshes, but with continued research into the processes and patterns of salt marsh change and a concerted effort to use that research to restore salt marshes offers a promising hope that salt marshes will be protected for future generations.